done just for, let's say, embedded software development. And now with the new Vitis flow, okay, we call this now an extensible platform. So that means is, okay, we can use our we can use our platform not also to be used for hardware accelerated based applications. Again, okay, the starting point is still the hardware, the XSA file. We use still the Vitis platform, but okay, it gives us the opportunity now by using this Vitis unified platform to create also object files, so kernels. That means is we do not have to use, in principle, the Vivado tool, so it can be more or less software based. So, but also we do support, let's say, the combination where we have the programmable logic and the AI engine flow, finally to create one image. Nevertheless, okay, we still need for the different stages. So for the, let's say, the Vitis engine flow and for the PL kernel flow, the different compilers. And we will address this later in this presentation. So the Vitis Unified Software Platform is an integrated development environment for development of embedded software applications. The Vitis environment keeps the features of the software development kit and adds more to the addressed requirements for heterogeneous computing. So we'll see the different domains. So we do support now the different domains as just one environment. Okay, we only need to include the different libraries. So the Vitis core development kit, okay, contains of the Vitis compiler and linker, which has embedded now the HLS tool, the kernel wizard, and the AI engine compiler. And to analyze our code, we have the Vitis analyzer, and we can also still debug our code. Also, AMD provides what we call the Xilinx runtime libraries, so they can be used on top of the platform. And the platform, okay, can be any type of platform. So the Vitis tool, Vitis Unified Software tool, is not only meant for Versal devices, but can also still be used for the Zynq devices or the MPSoC devices, Alveo cards, Kria, SOM modules, everything. So it's just one tool for, let's say, all the complete hardware, as long as there's an embedded, let's say, process based. So we do support all developers, including hardware designers, firmware, software developers, and AI developers. Also, hardware designers, okay, still they use the hardware tools, so they will use the Vivado tools. The software developer guys, okay, they will just use the Vitis tool, embedded tool. Application software guys, okay, they also use the Vitis environment, but okay, they will maybe using more sophisticated libraries. And finally, okay, the AI developers or data scientists, okay, they use the Vitis AI tool, but everything is now part of just one tool. So they all use the same tool flow, the same, but okay, the final result will be, okay, the different images or let's say output files, which can need to be loaded onto the target platform. So just give you, let's say, a quick look of a concept of building a Versal system. So we have on the right-hand side, we have the processing-based system. So this will be, let's say, our ARM core. And on the left-hand side, we have the programmable logic. And if it's applicable, also the AI engines. So we have a hardware platform, we have a software platform, and we can have, let's say, multiple systems or subsystems. So in this example, okay, we have 3 subsystems. But if you look at subsystem 1, okay, this one contains an AI engine block, and it contains programmable logic. And this programmable logic, okay, can be created by the HLS tool. So this will reside, let's say, in the programmable logic. And okay, from the firmware, from the software side, okay, we always have, let's say, the firmware-based parts. So to continue with this is that a subsystem, as we can see this here, this red box, okay, it's a combination of, let's say, the processing firmware together with some kernels and optionally with some AI kernels, programmable logic kernels. And everything will be what we call is then will be seen as what we call a graph. So this is how it will be called. So when you should ever attend the Versal AI training course, okay, you will notice that all the connections and all the applications, okay, will be called via graph. And graph is nothing more than, let's say, the interconnect between the processors. So we will have one AI kernel and we will have one HLS kernel. So an AI engine kernel in C++ program, we'll be targeting to an AI engine, while if we have an HLS kernel, okay, the target will be the programmable logic. So again, each subsystem will be divided and tested independently from other subsystems. So each of these blocks, so the AI, the PL, and the PS can be tested separately. And also the PL components of subsystems, they will be assembled by using the v++ link command. So we will use, to build up a one system, we have to add the processing unit, we have to add the programmable logic from HLS, and we have to add the AI engine created by the AI engine tool, and maybe programmable logic. They all need to be linked together. And then finally, they need to be packaged together by the v++ package command. Okay, and this one, okay, creates us the final, let's say, device or the image file just to download on our target. In case we have a platform, okay, this insulates developers from low-level details. So it will just focus on the application. It will also add, let's say, IP blocks, and it can be that your design contains, let's say, multiple IP blocks, such as maybe the NOC or the DDR controllers, or maybe some primary IOs. And also the software platform is usually generated by just using the Peta Linux tools, which also includes in the first stage bootloader, device tree, and also the operating system. So that will be the complete combination. And this is more or less how it looks, the flow looks like. So on top, we see the different, let's say, not behaviors, but the different designers. So we've got the ones, let's say, the data scientists or the AI engines. They use the AI kernels. We have people who write hardware based on C, so they create programmable logic kernels. Of course, we can also have RTL code. Okay, there we create the RTL kernels. And as an input, we need a platform. So we need to know what type of hardware, and also we need to know what type of processor to be used. So all these different areas, okay, they have their own, let's say, tools and resources, and they need to be combined. So these will all be the input towards the integration tool. So that means is that to integrate the programmable logic as well as the AI engines, okay, we need to link all objects together. And this information can come from the Vivado tools. The nice thing is also we can apply time constraints to our system. We can simulate our code, and at the end, okay, we will just generate the bit file just to be run on the device. On the other hand, okay, you would also like to do some emulation. So for each section of hardware, okay, we use we have the AI simulation, so we can simulate our AI parts. We can emulate our software, which is on QEMU, and we can also simulate our code by using the designing simulation tool for the RTL. So we have dedicated development tools for each of these domains, and also for the different persons. So as already mentioned, we have the AI engine tools, we have the Vitis tools, and we have the IP integrating tools. And as we can see now is that each of these domains, okay, produce different output files. So this will be a graph file, this will be an object file, a kernel object file, as well as for the HLS, as for the IP. And they all need to be linked together by the v++ link command, and then finally they need to be packaged. This will create then the device object output file. Also, we use the different compilers, but okay, AMD has chosen to use the GNU compiler. On the other hand, okay, for the ARM processor, of course, you're also able to, let's say, choose for the ARM compiler. That's also an option. So the AI engine tools, they are used to compile the AI engines, and also to simulate this design. So the AI engine compiler compiles the user code into a graph, as we mentioned. So that will be an lib.adf.a file, which then describes how the AI engines and programmable logic kernels will be connected together. It also calls the underlying kernel compiler, just to compile our code, which will be running on the AI engine. So for each AI engine has its own compiled code. And to simulate this, okay, we can use the AI engine simulation tool. So we are able to simulate each AI engine separately. We have also the Versal AI Engine C simulation tool, which is called the AI Simulator, and this includes also the models for global memory. So we can even simulate the DDR as well as the network on chip. So the NOC can be simulated. So this was also one of previous questions: can we simulate or can we emulate the NOC together with DDR? Yes, and the answer is yes, we can. And then we need to do the integration. So the VITES environment, okay, will integrate, let's say, the different processor cores together. And again, okay, we need therefore the packager. So this finally, okay, creates the object file, which then needs to be downloaded on the target. And as already mentioned, okay, we do support the run and debug flavor. So we can do hardware emulation, we can do debugging, we can do profiling. And then for those who are working with the MATLAB environment, okay, there's the VITES Model Composer. So the VITES Model Composer is a model-based design tool that enables you to do, let's say, rapid design exploration using the MATLAB tools. It will do automatically code generation. It supports the different libraries as well as for HDL, HLS, AI. And we can also import custom hardware and HLS or AI code. So with the VITES Model Composer, you can just create a design using optimized blocks. You can visualize and you can even analyze. So it has, let's say, different options and flavors compared to the VITES Unified Platform tool. It can do seamlessly co-simulate the AI engine and programmable logic together, and also automatically will generate our code. And we can also import custom hardware, AI engine, and RTL code as blocks using the Model Composer tool. But again, okay, if you're more interested, there, AMD offers the VITES Model Composer training courses. Yes, and then the last few slides shows you, okay, the different compilation flows. So we have here the three different domains. So the software domain, the acceleration domain, and the AI engine domain. So what we need, we start with the software development flow, is we need, of course, the compiler. So we need the cross compiler, probably because, okay, you run this, you compile your code, let's say, on an Intel-based platform to run this on an ARM platform. So that's where we can use the GNU tools. And if it's applicable, okay, we have the Xilinx runtime libraries. If you look at the accelerator development flow, that's where we have the kernel sources. That's where we use the VITES compiler and linker. And the final result will be the Excel bin file. Or for the Versal device, it will be the DSA file, as we call it, just to program the logic. And if you look at the AI engine development, that's where we have the AI engine source code with the AI engine compiler, and the tool will create here the AI engine binaries. And all this together, okay, comes together and will be addressed into one, what we call then configuration data object file, so a CDO file. So as you can see, okay, if you start doing development with the AI engines, you need to support, or you need to think about these three different domains. So you've got your software domain, the accelerator domain, and the AI domain, and everything has to be packaged together. So to conclude the development flow, okay, we have two questions for you. So the first one is apply your knowledge is to match the following design flows with the associated design. So we have a hardware-only design flow. So which one to be picked? We have a fixed hardware platform design flow, and we have an extensible hardware design flow. So I will make this available for you. And I think we address this slightly different. We say, okay, the hardware only design flow matches to which of the following designs? So hardware only, is this PL based? Is this PS plus PL based? Or is this PS plus PL plus AI engine based? So pure hardware design flow. Okay, I show the results, and indeed it is, and that's most of you have chosen, 77% says it's PL-based design. So yes, so the hardware-only design flow is related to PL-based design. Then we've got another one. I think we split this into 2 questions. So the extensible hardware, so the extensible hardware platform design flow matches to which of the following designs? Is it PL based? Is it PS plus PL based? Or is it PS plus PL plus AI based? So it's the extensible hardware platform. It's interesting. It's almost 50-50. Because probably PL based, okay, it's not an option because you already have chosen that one. So it is either PS and PL or PS, PL and AI. Okay. Well, I can tell you that slightly the majority had the right answer. It's indeed, it's PS, PL, and AI engine based. That will be the extensible hardware platform. And extensible means is, okay, you can load different applications running on the AI engines. If it's a fixed hardware platform, it will generally be the PS and PL. So just to give you the feedback of the other questions, okay, you see here the So the hardware design only flow is PL based. The fixed hardware platform design flow is PS plus PL based, and the extensible hardware design platform design flow is PS plus PL plus AI based. Okay, and then I think this will be an easy question for you. Okay, which of the following flows are supported by the Vitis Unified Development Platform?